Hello, everyone. We're happy to have Dr. Ashton Flinders to tell us about his research in Hawaii. Ashton is a research geophysicist with the U.S. Geological Service Volcano Science Center, currently assigned to the Hawaiian Volcano Observatory as a Presidential Management Fellow. Prior to moving to Hawaii in 2019, he was a Mendenhall postdoctoral fellow at the California Volcano Observatory. He holds master's degree in geology and geophysics from the University of Hawaii and ocean engineering, focusing on ocean mapping from UNH CCOM, where he worked on multi-beam data compilations in the Arctic Ocean with Professor Larry Mayer. He completed his PhD at the University of Rhode Island Graduate School of Oceanography, focusing on applications of high-performance computing to seismic tomography and 3D elastic wave simulations. As part of his current fellowship, he is currently on a 4-month detail to NOAA's Office of Ocean Exploration and Research. Please hold your questions till the end of the talk. And also one more announcement, next week we won't have seminar, so next seminar will take place on December 4th. And that's it. You can share your screen, Ashton.
Sorry about that. I went into a hot corner of my screen and put on the screensaver, which then meant I had to futz around and find my government ID to unlock my computer. Everyone can hear me?
Yep, you're good.
Okay, thank you. All right, so I'm actually not going to focus much on research today during the talk. I'm going to present an overview of the 2018 eruption of Kīlauea Volcano, as well at the end, if there's time, as a summary of some of the completed and ongoing research being conducted by members of the U.S. Geological Survey's Volcano Hazard Program. That's myself and some of my colleagues. Now, if you're wondering why the title slide says Kyle Anderson, it's because I want to acknowledge that I stole about half of these slides from a colleague of mine at the California Volcano Observatory. He was gracious enough to share them, but we'll just scribble out his name. I also want to mention 2 points which are important to keep in mind throughout this talk. First is that this really was an unprecedented eruption in modern times, both in terms of the volume and rate of lava erupted, but also with regards to the collapse of the summit caldera. And second, while the eruption ended just over 2 years ago, the data collected will be worked on for a lifetime. And we are really just beginning to understand the processes that occurred, why they occurred, and the implications of them. Now, I have a lot of videos littered through this talk, and hopefully they don't get too laggy. Now, one important message I hope you take away from this talk, all other science aside, is that long-term volcano monitoring really pays important dividends. This is a photograph of Thomas Jagger in his office in 1925. Jagger was the founder of the Hawaiian Volcano Observatory, which I'll refer to as HVO. And he founded it in 1912 under the belief that careful, long-term scientific observation and investigation are key to understanding and forecasting hazardous geological processes. And I'm proud to say that within the U.S. Geological Survey, that sentiment is true today as it was then. And that really, it was this long-term record of observations, more than 100 years at Kīlauea, that allowed the Hawaiian Volcano Observatory to respond as effectively as it did to the eruption in 2018. Now, Kīlauea Volcano is on the island of Hawaii, and the island of Hawaii is comprised of 5 separate shield volcanoes, with Kīlauea being the youngest. And you only see 4 of them there. The 5th one is up top, Kohala, out of view. Now, Kīlauea is, at least in recent history, the most active volcano on the island. And up until 2018, one of the most active volcanoes in the world. Importantly, it's also one of the best monitored volcanoes in the world. As I said, HVO has been monitoring Kīlauea for more than a century. But despite this long-term monitoring, there's some really fundamental questions that remain. For example, as you see on the slide, what causes dangerous explosive activity? Where is magma stored and how much is there? How is the summit connected to the rift zones? And what is the interplay between tectonic and magmatic forces? Now, the summit's on the left-hand side of the figure, and it's connected to what we call the East Rift Zone. And a rift zone on a volcano is just a zone of weakness in which magma can flow relatively easily or intrude. If I zoom in on the summit, I'll start by showing you where the Hawaiian Volcano Observatory is. Or I really should say was, because following the eruption in 2018, it's been pretty much uninhabitable. And so if you can see my cursor right there, that was the Hawaiian Volcano Observatory. The building is still there, but as I said, we evacuated it in 2018. And it was perched right on the rim of the caldera, which really was a fantastic viewing location. But given the damage that occurred, perhaps a little too close to the caldera, which is outlined here in red, shaded here in red. Now, within this caldera is the Halemaumau crater, highlighted there in red with the blue line around it. And within that crater was a lava lake. This lava lake was active from 2008 until it drained during the eruption in 2018. The lake was several hundred meters across, and its level rose and fell with pressure changes in the magma reservoir beneath the volcano. We'll talk about this later. The broader caldera has filled with lava and undergone collapse repeatedly over geological history. The Halemaumau crater, that intermediate size feature, is also dynamic, and it last dramatically changed in 1924 when it doubled in size. Now I'm going to show you another picture of the crater and the lava lake taken from a different angle, just to give you a kind of an actual photographic perspective. And it's taken from a helicopter at the approximate location of that red line, or that red arrow, looking in that direction. And so up until spring of 2018, this is what you would see. This was actually taken in April of 2018, so just a couple weeks before the eruption began in May of 2018. And so you see the Halemaumau crater, you see the lava lake within it, and actually here you actually see the lava lake is so full that it's overflowing onto the crater floor. And we'll get into this a little bit more later. Now at Kilauea, magma rises up beneath the summit and it passes through a series of crustal reservoirs, after which it flows down into the East Rift Zone. Since 1983, magma has migrated down the East Rift Zone to the downrift vent Pu'o'o, which is shown in the photographs here on the top. And this vent has been erupting semi-continuously for 35 years. And typically, magma would migrate downrift from the summit, where it would reach the surface near Pu'o'o and be erupted. And these lava flows would then move downslope to the sea. And this was pretty much the standard behavior over the last 35 years prior to 2018. Now, the lower East Rift Zone, where the eruption actually occurred in 2018, is further downrift, towards the coast on the far right-hand side, circled there in blue. There have been no lava flows in the lower East Rift Zone since about 1961. Eruptions in the lower East Rift Zone in 1955 through 1961 lasted on the order of 1 to 3 months, except for 1961, which was mainly a summit eruption and then had about 3 days of kind of middle to lower East Rift Zone activity. So not quite in that blue circle. The photograph on the top is from eruptive fissures during the 1960 eruption. And it's going to look very familiar to some of the activity we'll see in 2018. So now let's imagine we take a cross section along the path of the rift zone, so right along those red arrows. And we draw a very simple cartoon of the crustal structure of that rift zone. We'd see something like this. And let me stress that this is not to scale at all. Process-wise, what happens is magma rises up from the mantle, shown in the lower left of the slide, to supply Kilauea. And this magma passes through a series of storage reservoirs at the summit. The most shallow of these reservoirs is likely about 1.5 kilometers below the summit. And it's directly connected to that lava lake that we looked at earlier. After it reaches the reservoir, it could then flow about 20 kilometers downrift through the East Rift Zone, where, as I said, ever since 1983, it's been erupting near that vent Pu'o'o. Now, not to spoil the ending, but as you may have heard, if you went around, things changed pretty dramatically in 2018. Instead of that magma erupting at Pu'o'o, magma intruded further downrift and erupted in a residential subdivision called the Leilani Estates. This was a further 20 kilometers away. So just to reinforce this scale, because I think it's pretty remarkable, the reservoir is about 1.5 kilometers deep, but during 2018, it was feeding a sustained 3-month eruption over a path of more than 40 kilometers away. So starting in the spring of 2018, we had indications that magma was beginning to back up in the plumbing system beneath the summit and Pu'o'o. One of the ways this was monitored was by measuring the distance between locations on the opposite sides of Pu'u'o. So here's Pu'u'o, using two GPS stations. So a GPS, say, here, and a GPS, say, here. And you can imagine that if magma starts backing up and the pressure beneath the vent or in the rift zone uprift of the vent towards the summit starts increasing, the surface will begin to deform and the distance between these two GPS locations will increase or lengthen. And that's exactly what we saw from January 1st to April 29th of 2018. Starting in mid-March, the distance between these two locations, about 1 kilometer apart on each side of the vent, started to increase. Then in April, it began to really accelerate. So this is all pre-eruptive signals that we were actively monitoring. And as a result of this deformation, HVO issued a warning that a new vent could either form at Pu'u'o or along adjacent areas of the East Rift Zone. Now, at the end of April, things really became dynamic. At 2:15 p.m. on April 30th, something completely unexpected happened. Something completely unexpected is happening on my porch. There's 3 neighborhood dogs, but that's aside. All the magma rapidly drained out of Pu'u'o, and Pu'u'o collapsed. Magma rapidly exited the system right under Pu'u'o and intruded downrift into the lower East Rift Zone. And so the photograph on the upper left, this one right here, is what Pu'u'o typically looked like when filled with magma. So this is the actual crater, the subcrater, and this black stuff right here is actually viscous magma filling up that crater. Now the photo on the lower right is after magma evacuated downrift and the decreasing pressure could no longer support the edifice and the vent collapsed. Now this is that same time series, but it extended an additional few weeks into May. And what you can see is the inflation that we saw earlier in the last slide as magma pressure increased throughout April, and then the rapid deflation as the magma intruded downrift and drained away from the Pu'u'o vent in early May. This is a map of the East Rift Zone. So Pu'u'o is circled here in blue. And prior to the eruption breaking out in the lower East Rift Zone, HVO was able to detect an increase in the number of earthquakes migrating downrift, as well as broader scale ground deformation. Both of these observations suggested magma was migrating towards that residential subdivision, the Leilani Estates, right here, which at the time had about 1,500 people living there. So as a result of the deformation and the seismicity, this is following the collapse of Pu'u'o, HVO issued a warning that an eruption was possible. Now, there were some pretty obvious signs of ground deformation occurring along the path to Leilani Estates and within the subdivision itself. And here are some examples of those deformation signals. But in all honesty, these photos were actually taken on May 17th, I believe, so about 2 weeks after the eruption began. But even in late April, the beginning of these cracks were noticeable. And so those are some early cracks on May 2nd, before the eruption began. And some of these cracks were also emitting steam and eventually sulfur dioxide. And it's not hard to imagine what's going on. Magma is migrating downrift and it's shallowing. And it's beginning to reach the surface. And as it does so, it vaporizes groundwater, creating steam, and it also fractures the shallow surface. So this surface deformation, particularly when it's small cracks like this shown on the left, can be really difficult to observe when they're in the jungle or the rainforest. But on a nice, straight, flat length of road and asphalt, it becomes pretty noticeable. And it was one of the main ways we were monitoring pre-eruptive signals and where eruptions would be ongoing in the future. And so you see right here, there's a little mark. So what people were doing was early on, they were putting spray paint or chalk marks across it, measuring the distance, and using that as an early sign of active deformation. Now on May 3rd at 5:15 p.m. local time, the eruption actually began. And it began with a long linear lava-filled fracture, which we called a fissure, breaking out in Leilani Estates. The initial eruption was a little bit different than the later part, and over the first week consisted of a series of small fissures stretching over about 7 kilometers. And while these fissures erupted lava fairly high, what we call fountaining, there was significant gas being emitted. These initial fissures did not create really large lava flows. And you can see it just, this is in Leilani Estates, and it's right across the street and in someone's backyard. Here are a few more examples of what these fissures early on look like and the flows look like. The bottom left is a video of a fairly slow moving flow, or a rubbly flow that's moving down a street in the Leilani Estates. This is in real time, not sped up or slowed down. Again, in the lower right side, you see a relatively small fissure with just a very small localized flow around it. In the upper right, there's another small fissure through the forest about the size of a house, which you can see for scale. And we're going to look at this top left photo, but we're going to look at it as a video. Now, for the most part, these fissures created fairly local lava flows and hazards. And activity would alternate up and down the rift between them. Geochemists were sampling this lava as it was being erupted and doing really amazing and rapid lab analyses, which allowed us to know that the early lava, the first material that came out in the beginning of May, was really evolved. It was really old. So they were able to tell that what was being erupted was not the fresh 2018 magma from the summit or Pu'o, but likely older magma from the 1950s or early 1960s. And so magma that was stored in the crust for more than 60 years and was being pushed out as new magma migrated downrift. This magma was cooler and more viscous, and it didn't create the large, fast-moving pahoihoi flows, really fluid flows that we would see later. And I just put this in at the last minute. This is one of those geochemists grabbing a sample of rock for lab analysis with their shield in tow, decked out in Kevlar. Now, this is a thermal map of those early fissures. This was made on May 6, so just a few days after the eruption began. These maps were a routine part of our monitoring effort. Several times a week during the eruption, a geologist, as you see in the upper left, I think that's Matt Patrick of the Hawaiian Volcano Observatory, would get in a helicopter and he'd use a thermal camera to take photographs of the fissures and the advancing flow fronts. They would then mosaic together these thermal photos and georeference them. And so the white areas are hot, i.e. lava flows and fissures, and the black areas are cool. And each of these red numbers is a different fissure. And these fissures were numbered in the order they appeared. So as you can see, there's on May 6th, a few days after the eruption began, there's already 10 fissures that have broken out. And again, what you'll see is for the most part, for most of these fissures, they just have very small lava flows that are really just local to the fissure itself, and they're not very productive. But at this point, there are some larger lava flows, or what seemed at the time larger lava flows, being produced by that 8th fissure to erupt, which we'll just call fissure 8. And so early on, fissure 8 really begins to dominate. And so this is just a few days after the eruption onset. That's that larger flow that we saw in the thermal map earlier, and it's basically just tearing through the subdivision, destroying homes and propagating forward. Now, I'm just going to briefly mention it, but I won't talk about it in any detail more than this slide due to time limitations. But as if things weren't busy enough, on May 4th, the largest earthquake in Hawaii in 43 years happened. This was the biggest earthquake since 1975. It was a magnitude 6.9, and it was felt over 500 kilometers away, so throughout all of the Hawaiian Islands. And during this earthquake, the whole south flank of Kīlauea, so this is the coastline, or this is the ocean, this is the coastline, this is the summit up here. The whole coast slipped about 0.7 meters. And if you're interested in the earthquake, please ask me about it at the end. Now, while all this eruptive activity was going on down in the lower East Rift Zone, the summit of Kīlauea is also undergoing its own changes. In between the collapse of Pu'o on April 30th and the first fissure breaking out on May 3rd, the summit is starting to subside, it's starting to sink down, as magma is withdrawn from the summit reservoir to move downrift. And this subsidence really started to accelerate after the eruption began. So you can imagine where magma is being removed from Pu'o, it's going downrift, and in turn, magma is being removed from the summit to go down to Pu'o and eventually to the lower East Rift Zone. And we could observe this in near real time through GPS. So the top left figure is a map of GPS vectors, and you'll see that they're all pointing inward. So the summit is deflating down, kind of centered over the Halemaumau crater. And then we were able to do that in pseudo real time. And then we were also doing it through interferometric synthetic aperture radar shown here on the right. So each one of those fringes represents displacement away from the satellite. Now, the photograph in the background is from a camera pointed down into the summit lava lake taken in early May. So kind of similar to what we looked at earlier, except the lake's already drained down a little bit because of the magma being removed. And so remember the photo I showed you earlier, it was really high, and that was because the pressure was really high in the system. But starting on May 1st, after Pu'u'o collapsed, the summit lava lake started to drop, just like draining water out of the bottom of a bucket. And on May 4th, that rate really accelerated, and it started draining at about 2.2 meters per hour. And remember, this lava lake's several hundred meters in diameter, so it's an amazing amount of magma that's being removed. Now, in the upper right is a thermal camera time lapse from May 2nd to May 8th, so basically the first week of the eruption, with color representing heat. And what you're going to see is the surface of the lava lake drop over that 6-day time period. As the lava lake level drops, it's destabilizing the walls of the conduit, and pieces of wall rock are going to start falling in and make little hot spots on the surface of the lake. Now, the lake ultimately drained about 1,000 feet before it vanished from sight on May 10th. So really amazingly quick when you start thinking about it. You know, something several hundred meters wide and 1,000 feet deep, draining away in about a week before it disappeared from sight. Now, that's not to say it drained away completely. That's just when we lost visual evidence of where the level of the lake was. And again, this is directly connected to the shallow summit reservoir, which is probably, you know, 3,000 to 5,000 feet deep. So this is a time series from April 29th up until May 16th, with each red dot on that time series representing the height of the surface of that lava lake, measured by a laser rangefinder next to the thermal camera. So this is that thermal camera and also rangefinder that's measuring that distance, but also taking those thermal photographs that we looked at earlier. And when it starts to drop, we notice something. We notice it's dropping at a pretty constant linear rate. And in volcanology, as a lot of things in our science, constant rates like this are a bit unusual. Things are always changing, things are dynamic. And so when my colleagues saw something really steady like this, it gave them a bit of pause, but also a little bit of excitement. It meant that we could do some really simple analysis. We could draw a line through it, and we could ask, well, what happens next? And so while all this was going on, the question we started to ask was, when is the lava lake going to reach the height of the water table, which is about 600 meters above sea level, shown by this yellow star. And this dot right here is the last measurement of the lava lake before we lost the sight of it with the thermal camera. So between here and the water table, we really didn't know, how fast it was dropping. So who cares about the water table, and why does it matter? Well, at the time, just 2 years ago, the prevailing wisdom was that the interaction with the draining lava lake and the water table causes explosive behavior at the summit of Kīlauea. The idea being that if you have a long-lived lava lake and magma conduit, which has superheated the ground in an envelope around the conduit, like this first diagram here. So this is the water table and water, this is the conduit, and this is kind of this superheated envelope around the conduit. This acts as a barrier between groundwater and the lava, and they can never interact. The water just vaporizes to steam before it can reach the lava or magma. But if the lava lake drains below the water table, and the wall rock starts to collapse, like we saw in that thermal video, then you begin to have a situation in which you have sealing from collapsed rock and really rapid volumetric expansion of heated water and large explosions. And there's a precedence for this. This is Kīlauea in May of 1924. And similar to 2018, there was a lava lake in 1924. And there was a dike intrusion into the Lower East Rift Zone in 1924. So very, very similar analogy to what we had in 2018. And in 1924, the lava lake drained and explosions happened just like the one shown here. And these were substantial explosions, and they lasted over several weeks. These explosions threw blocks of rock that weighed several tons and were up to 2 meters across, more than a kilometer. I've been hiking out in some of these areas, and you come across blocks from 1924 explosions that are the size of Volkswagen Bugs. Ash from these explosions fell across a huge range of the Big Island. Even little gravel-side pieces of rocks were deposited as far as 3 kilometers away. So this was a major hazard that the Hawaiian Volcano Observatory was concerned about. And as a result, on May 8th, HVO released a preliminary summary hazards assessment in which we said the potential for Summit lava lake surface to drop to or below the groundwater table raises the strong possibility of explosions. And this had big implications both for us at the Hawaiian Volcano Observatory, who were partially still operating out of our buildings there, but also for the national park. So Kīlauea Volcano is in a national park. Now, while we didn't observe the massive explosion seen in 1924, beginning on May 4th, we did begin to have small explosions at the summit and ash venting. These were triggered by rocks falling from the walls of the lava lake conduit that had become destabilized as the lake drained away, and likely falling onto the lake's surface, similar to what we saw in that thermal time lapse, but on a much larger scale. And from May 16th to 26th, there were 12 larger explosions, but still not anywhere as large as 1924. During this time, the summit continued to deflate. And this looks similar to the lake level surface height we looked at earlier, that time series taken from the laser rangefinder. This is actually a measurement of ground deformation at the summit from a tilt meter. And so time on the x-axis, and this is microradians of tilt at a summit station on the y-axis. And so you can think of this as a proxy for inflation and deflation of the shallow summit magma reservoir. As that red line goes up, the reservoir is inflating. And as the line goes down, the reservoir is deflating. And you can see that the overall trend was deflation at a fairly constant and fairly large rate. And that's because of all that magma that's being removed to feed that lower East Rift Zone eruption. After the lava lake disappeared, and beginning with the first 12, so that's the lava lake disappearing right here, and beginning with the first 12 of those explosions between the first 12, which started on May 16th, we began to observe kind of a stair-step-like pattern in summit deformation. We get a rapid inflation followed by a gradual deflation. And each one of those inflation periods is correlated with one of those explosions like we saw earlier. And so these explosions and collapses became semi-periodic throughout May. And they occurred anywhere from every 8 to about 45 hours. And aside from the explosion and ground deformation, each event was also associated with a very long period seismic signal. While the explosions in May weren't as large as the ones that were observed in 1924, they did have fairly significant ash columns. So some of these ash plumes reached as high as 30,000 feet. The explosions from these events waned in June and basically stopped. But the collapses and these inflation-deflationary events, which I'll just call collapse events, continued throughout the rest of the eruption and still stayed fairly periodic. Now back in the lower East Rift Zone, fissures were continuing to erupt. And so this is May 21st. I think this is fissure 20 or 21. I forget what the title slide said. After the talk, I'll post a link to our multimedia library in the chat so you can take a look at these in higher resolution and at faster frame rates, because they really are quite astounding. So as we talked about, in early May, the lava that was erupted was relatively cold. It was evolved, and it was viscous. And because of this, the lava flows from those early fissures didn't flow very far. But by mid-May, that really changed, and the eruption rate really picked up, and we started seeing fast-moving flows which reached the ocean. So in the lower left-hand corner, you can see the first of these ocean entries. So these are these eruptive lava channels that are starting to form. This is the coastline, and then this is the ocean. And by the end of May, these really impressive lava channels were starting to become well established. So here's the beginning of that channel on the right. And we'll just take a quick look at the video there as this channel began. So this is May 19th, so about 16 days after the beginning of the eruption. And this is largely forming from lava that's coalescing from those fissures and flowing downslope. And this is just an example. This is actually taken in June of 2018, so a little bit later on. But this is an example of one of those ocean entries. So magma, lava is going into the ocean, and it's creating these really energetic explosions as it interacts with seawater and volumetric expansion as the seawater goes to gas. It's also producing these plumes of, it looks just like steam, but it's actually much worse. So it's superheated steam, but it's also a mixture of volcanic glass. We call it lays. Really, really horrible to breathe in. So on May 27th, activity really began to focus at Fissure 8. And this became the main source of most of the lava flows in the lower East Rift Zone throughout the rest of the eruption. So after the 27th and all the way through the beginning of August, Fissure 8 is where most of the magma was erupted. And much of this was erupted as these really high lava fountains, which erupted tephra as high as 80 meters into the air. And then this tephra landed back down and it gradually built this cone. And so this is a dark shot, but we'll see a video of this in the next slide. And this is that cone. And then some of this lava is just being erupted out into the channel, but some of this lava is actually being erupted into the air, landing back down as splatter, and then coalescing and forming lava flows. So here's that cone of Fissure 8. And whenever I show you a video like this, I really want you to remember that none of this was there before May. This was a subdivision with forests and houses and people who had retired to this area, people who had lived in this area for 40 years. This fissure fed that channel we saw earlier, which you can see in the video in the upper right here. And this lava channel extended for more than 10 kilometers to reach the ocean. These fissures, besides just the lava hazard they were producing, also produced an amazing amount of volcanic gas. So these were outputting about 40,000 tons of volcanic gas a day, which is an absolutely huge number for Kīlauea. It's much higher than before this event started, which might have been around a few thousand tons or a few hundred tons, depending on the day. And this is despite Kīlauea having been erupting since 1983. These were still the largest amounts of volcanic gas being produced. The gas emissions strongly affected the air throughout the island. So people, depending on where you live, were recommended not to go outside, not to exercise in the air, or exercise outdoors. And the air quality, the gas, it was so much gas that it actually affected the air quality as far away as Guam. This is just another video of Fissure 8 on top, showing some of that fountaining. So really energetic, much more fluidal than the magma that we saw being erupted in the earlier part of eruption. So this is that hotter Pu'o magma that's now come out. And because of this, it's able to form these really fast moving lava flows. The video on the bottom is just downslope of Fissure 8, where the coalescing lava from the fissure begins to get channelized. Here's another quick shot of Fissure 8 on the top right-hand corner, feeding these lava channels. These channels ended up becoming very stable and existed for most of June and July with relatively little change. They actually eroded down into the subsurface, dozens and dozens of meters. Now, this is just a quick aside. As mentioned, these flows reached all the way down to the coast, and most notorious to a place called Vacation Land and Kapoho Bay. This is Kapoho Bay in the foreground. And this was really an amazing snorkeling and swimming spot, kind of world-renowned and renowned throughout the Hawaiian Islands. Unfortunately, that bay quickly filled, and it destroyed the bay and the natural wonder of that snorkel spot, but also hundreds of homes on its way to the ocean. It actually built out a huge lava delta, which we'll look at in the next slide. So this is an animated map, or it will be an animated map, showing how the lava flows primarily from Fissure 8 evolved through the eruption. It starts in early May, as you see the breakouts in the Leilani Estates, but also some breakouts in fissures downrift. And after that lava channel from Fissure 8 really gets established right there, that's that Fissure 8 lava channel, infilling Kapoho Bay. What you'll mainly see for the rest of the eruption is the filling and broadening of this ocean entry in this coastal region as it's being filled by, or as it's being fed by these channels. One question we often get is how much lava was actually erupted. And so this is just going to go for a couple more seconds. And one of the reasons that's very difficult to answer is, you can look at how much lava was actually made it to the ocean entry. So this is all part of a new lava delta that was formed, a new coastline. And subaerially, we can estimate the thickness and get a volume. But if it disappears into the ocean, we really have limited ability, at least within the Hawaiian Volcano Observatory. So I just decided to sprinkle this in at the last minute last night. How far and how thick were the flows offshore? There is existing multi-beam data. So there's varying and limited pre-2018 multi-beam data sets. Actually, if you talk to Paul Johnson at CCOM, he probably has a good idea of probably what's out there. And synchronously enough, the Nautilus was out here in August of 2018. So during the very tail end of the eruption, but there were still some flows being output, and they collected some data. And then actually the Rainier, NOAA ship Rainier, was out here in September of 2019, and they did a really amazing hydrographic survey, and that's this data here on the left. So potential UNH CCOM Masters Project, PhD chapter, I don't know if anyone's interested in looking at changing geomorphologies between those two, that 1 year between August and September, or figuring out a really quantitative way to estimate the pre-eruptive seafloor surface and get really well-constrained eruptive volume rates out to sea. There's some interesting channel features. I think there's a really wealth of projects that could be done with some of this data for an interesting student. Okay, so now going back to the summit again, around the time that activity focused on Fissure 8, the vent at the summit became largely blocked. The explosive nature we observed in mid-May stopped, but the collapses continued to occur. And this is a time-lapse video that I'm going to show you from the old Hawaiian Volcano Observatory building looking out over the caldera. And it spans from about mid-April to the beginning of August. And so here's the lava lake that we looked at earlier. And you're going to see a few things. You're going to see overflows from the lava lake in April. And you'll see May explosions that we looked at in those videos. And you're also going to start seeing local subsidence. So you're going to see dropping down of the area right here around the former lava lake. Then in late June, you're going to start seeing subsidence of the entire region. And so I'm going to play this video twice. So those are the explosions. And you can see the background starting to drop down. And then you see the broader scale subsidence dropping down. I mean, it's really, really kind of amazing to, if you had seen it, what it looked like before and what it looked like after. So I'm just going to play it one more time. Give myself a chance to drink some more coffee. It's 10:30 a.m. in Hawaii. We had a GPS instrument on one of those blocks that started dropping down initially. And it recorded up to 30 feet of vertical drop in just one of these events. And this time lapse makes it look semi-smooth, but really it was an episodic kind of behavior associated with those stair-stepping tilt patterns we looked at earlier. So during the eruption and the summit collapse, we also flew drones over the summit as often as weather would allow. And each time we did, we built a map using structure from motion and an elevation model of the summit. And that allowed us to quantify what we just saw. Play that one more time. So this is an animation of a series of those structure from motion drones, DEMs. And one more time, going back to the beginning so I can point out some things. So this is the Hawaiian Volcano Observatory right here. This is Kīlauea caldera, this broader feature. This is the Halemaumau crater. The lava lake was in here. It's hard to tell, but right here is an old parking lot. It's been closed since, it had been closed since 2008, but it was the overlook parking lot where you could look into a portion of Halemaumau crater. And this little spaghetti line is a road that went around the caldera. And so you can imagine how close the HVO buildings were and the damage that they were sustaining just from this downfaulting. Now I'm going to show you, this is a cross section of deformation compared from April 2018, that's the blue line, to August 2018 after the eruption ended. And what we saw was more than 500 meters of subsidence in some of these areas. I'm also going to show you a few photos, and they're photos taken kind of near where that road and parking lot were. So at the approximate location of this arrow. And so the deepest point of the caldera is off to the left. And these are some of these huge, massive, coherent blocks that just slumped down during the collapse. It's just kind of one giant piece. And it's hard to tell, but there's this little gray patch right here going across the screen. That's actually part of the old road. And so here's another angle of it. This is just a giant coherent block. And here's the road, still intact for the most part. You can still see the yellow lane markers on it. And so as I mentioned, this motion was not continuous. The caldera was not smoothly subsiding down. It was kind of subsiding in these steps. And I showed you that inflation-deflation time series before, where we saw the step changes associated with each collapse event, highlighted there by those dashed lines. And this is a similar time series, but this is just 2 weeks, from July 2nd to July 16th. Now, for an individual collapse event, which for the events in May also had that explosive component, if we looked at the GPS stations in and around the caldera, what we would see was the caldera dropping down episodically, with the whole caldera floor moving down tens of feet during each one of these events. But if we looked at the tilt sensors, so GPS is on the top showing those episodic down droppings. Tilt, like we looked at earlier, is in the middle. And if we look at the tilt, what we actually see is the ground motion moved more or less simultaneously, but as an inflation upward and outward, and then the slow deflation. So it was a little weird at the time and a bit counterintuitive to have the GPS showing these down drops, but the tilt showing this inflation. And these collapse events were highly correlated with seismicity, which I'm showing in the bottom left figure in terms of earthquakes per hour. So looking at the seismicity, what you see is each time one of these collapse events, leading up to one of these collapse events, you have an increase in the total amount of seismicity. And then each time one of these collapse events happens, that earthquake rate drops almost to zero. And then the earthquake rate slowly ramps back up again until another collapse event happens, and we go through this cycle again. This really was a tremendous amount of seismicity, with upwards of about 700 earthquakes leading up to each collapse event. So, remember, these were happening on the order of about every 20 to 30 hours. So you're having 700 earthquakes in that time period. And then this would culminate with the actual collapse event, which on average released the amount of energy equivalent to about a magnitude 5.3. And so in total, there was about 62 of these collapse events. And so you can imagine we had about 62 5.3 earthquakes over the course of 3 months. So now, what was causing this subsidence seen in the GPS data, but the simultaneous inflation and gradual deflation seen on the tilt meters? Well, what was really happening was that the summit reservoir was slowly depressurizing as magma was being withdrawn to feed the lower east rift zone. Just like in the beginning of the eruption, we saw all this magma flowing out, and as this flows out, it depressurizes this reservoir. Eventually, the pressure decreases so much that the reservoir can't support the weight of the overburdened caldera, and the caldera crust collapses inward, compressing the reservoir. And this rapid compression of the reservoir actually causes the reservoir almost pseudo-simultaneously to expand. And it's kind of similar just to taking a balloon, blowing it up, tying it off, and then poking your hole in it. The balloon expands everywhere where you're not poking your finger into it. And so this causes the reservoir pressure to then stabilize eventually, but magma continues to be withdrawn, and the process eventually repeats itself. And so that's a really quick summary of what happened. And honestly, just as quickly as the eruption began, it ended. I always felt like kind of ending the talk here on the slide was a little bit anticlimactic, but the eruption at the end was kind of a little anticlimactic. Just as quickly as it began, it ended. The inner event time between these collapses became longer in the end of July until on August 2nd, we had what would be our last collapse event. We didn't know it at the time. We kind of just kept sitting around waiting for another collapse event. The rate of earthquakes began to increase soon after that last collapse event, like we had observed over the past 3 months. But within a few days, by August 4th, so 2 days after our last collapse event, the earthquake rate kind of relatively plateaued, and the seismicity just flattened without another collapse event happening. And without those collapse events, part of which that pressure was driving eruptions down in the East Rift Zone. Similarly, by the end of August, the activity from Fissure 8 was waning. So this is actually taken in early September, about a month more or less after the last collapse event. But you can see that by September 4th, Fissure 8 is really just kind of a sputtering shell of what it once was. And so, originally the lava was filling up this entire cone and outflowing in tremendous amounts, and now it's just localized to this little spattering section. So I won't go too much into detail on these, but these are just some numbers that I think are important to keep in mind. These were preliminary last year. They're probably better refined numbers now, but I couldn't find them last night. So about 1.2 kilometer cubed of bulk material erupted. There was 875 new acres of land that was created from the ocean entry. So that's 875 acres of lava delta that was formed, in places like the filling of Kapoho Bay. It was Kilauea's highest sustained lava discharge and volcanic gas emission rates observed historically. There was more than 60,000 earthquakes throughout the island. That's including this magnitude 6.9, which was the largest since 1975. There was more than 700 structures, that's buildings and farms and outbuildings that were destroyed. Several months-long evacuation. There was extensive damage to the national park. The caldera downdropping more or less caused the destruction of the Hawaiian Volcano Observatory buildings. I mean, they're still there, but basically been red tagged by FEMA as uninhabitable, and we're not moving back. And it's really uncounted millions in economic impact. And so with some of the remaining time, I just want to highlight a few research projects that have been performed by my colleagues and myself since the eruption ended. So one of the questions that I thought was really interesting from the beginning was what caused the inflation of Kilauea's magmatic system and the subsequent failure and downrift dike propagation? Why didn't magma continue to erupt at Pu'u'o? And so this is research I performed, published this year. Starting in March of 2018, we actually saw 3 swarms of lower crustal earthquakes that were observed beneath the summit. So this is time on the x-axis and depth on the y-axis. And what you see is these lower crustal earthquake swarms here, here, and here. Each one of these dots is an earthquake colored by depth. So these are between 4 and 12 kilometers. And this is in one of Kilauea's lower crustal reservoirs, so not that shallow one that's connected to the lava lake. We also saw those high lava lake stands and overflows in April, and associated with that was increasing pressure as seen by increasing seismicity in the connection between the summit here and the East Rift Zone. So this is this connector. And so what my co-authors and I propose is that these deep crustal earthquake swarms were actually indicative of short-term increases in magma supply to Kilauea's deep reservoir. And this short-term supply, increase in supply, helped drive increased pressurization. I was going to show this movie, but I'm running out of time, so I'm going to skip it. So while I'd love to say that that hypothesis I just presented for pre-eruptive pressure increases is the only one, that would be a lie. My colleague, Matt Patrick, one of HVO's amazing geologists, completely disagrees with me. We don't agree on this fact at all. And he similarly proposed a mechanism in which a gradual restriction in the flow of magma out from Pu'u'o, so this is Pu'u'o down here on the left, this right here is the conduit from the summer. This is actually Pu'u'o's little reservoir, and this is Pu'u'o's lava lake, and this is where lava had been erupting. He proposes that it was a restriction in this conduit here, which caused magma pressure to back up here and eventually increase the pressurization enough where the dike propagation happened. And so we know the system was pressurized, but whether this increased pressurization was a bottom-up process, as I proposed, or a top-down process, as Matt proposed, is unresolved. Now, with regards to what led to the downrift dike propagation and why didn't magma continue to erupt at Pu'u'o, in that same paper of my co-authors and I, we proposed that a magnitude 5.3 earthquake, so this is time here, 2016, 17, and 2018, a magnitude 5.3 earthquake beneath Kilauea's south flank in June of 2017 caused dynamic stress-induced fracture, or in other words, this earthquake caused a weakening throughout the system to dilatational crack growth. And this weakening was greatest near Pu'o. And we can observe this by looking at changes over the 3 years prior to 2018 in seismic velocity. And so what I'm showing here is relative seismic velocity at 3 locations: at the summit, at the East Rift Zone in green, and at the Southwest Rift Zone, another one of Kilauea's rift zones, in yellow. And what we see is, we see that in the East Rift Zone, we have this really quick drop off in co-seismic velocity, indicative of this weakening of crustal fracture, and then a slow post-seismic recovery, but not a complete recovery to the baseline preceding. And so it's my hypothesis that whatever the reason for increase in pre-eruptive pressure, whether from a constriction or increased source material, when this increased pressurization was combined with pre-existing weakness from the 2017 earthquake, we may have kind of had a perfect storm for downrift dike propagation. Another interesting story is big eruptions can start small, and you can kind of tell in real time. We know the chemistry of lavas can provide critical information on the underground sources of magma, the eruptive conditions, temperature, and other physical properties which will affect how the lava flows when erupted. Unfortunately, kind of prior to 2018, these analytical techniques were typically slow and leaving these sorts of analysis mainly for retrospective tools only. In 2018, during the eruption, Cheryl Genzecki at the University of Hawaii and HVO geologist Lopaka Lee developed a really novel analytical procedure to characterize the geochemistry of lava within a few hours of sample collection. So this allowed them to track lava compositions, estimate eruptive lava temperatures, and then use this data to inform the response chain to changes in eruptive conditions. And so just an example of that is, this is that cartoon cross-section again of 2018 dike, how it impinged on probably these older pockets of 1955 magma. And this really affected that early onset of the eruption, or the early first few weeks of the eruption, when that magma was pretty sluggish and slow. And depending on where these eruptive fissures were coming out, they could impinge different older crustal bodies. So on the left is a very fluid basalt from fissure 20 on May 20th with these high fountainings, and this would lead to those large lava flows. But this is fissure 17 in this panel, and this is only 800 meters away, and it's erupting a much more evolved andesite because it's pushing out some of that older magma. So what about the summit water table and the big explosions? And the possibility of those large 1924 style explosions. So this was also really amazing work that happened in real time during the eruption. While many of us were worried about the interaction with the falling lava lake and the water table, 2 of my colleagues from the USGS in Menlo Park, Paul Hay and Steve Ingebrigtsen, were able to use modern quantitative hydrologic modeling supplemented with hydrogeologic data from a water well at the summit to show that, contrary to expectations, liquid water inflow into the drain conduit would likely take years owing to the inability of the liquid water to transit that zone, that high temperature envelope of very hot rock surrounding the conduit. And so this is a time series in this panel of time in years and inflow to that magma conduit in terms of kilograms per second of liquid water. And what you see is it really takes several years before you get any of that water infilling. And so using this data during the eruption, this actually put us much more at ease about the lack of those 1924 style explosions. What about all those summit earthquakes? As I mentioned earlier, those summit collapses were preceded by up to 700 earthquakes over a few days. And so, in real time, or kind of just through standard locations, this is what that seismicity looked at. So this is a week of seismicity at the caldera. So this is the outline of the caldera right here. 2 of my USGS seismologist colleagues, David Shelley and Wes Thielen, used high-resolution methods to detect and precisely locate more than 44,000 of these earthquakes from late April to early August. And they found that the location patterns of these earthquakes revealed numerous seismically active structures, both on the boundary and within the collapsing zone. So in these panels, this is the caldera. This white line is the Hawai'i crater. This is a plan view, and this is a cross section in depth. And what you see is you see all this seismicity, and it's really just located along these ring faults around kind of intermediate to the larger caldera structure. And this is pretty much what those collapses were sliding down on. And you can see this view of that seismicity and these faults in depth section as well. And they hypothesized that most of these events were generated by a combination of fault slip and crack closure as those surface rocks collapsed into the underground region that was previously occupied by magma. And last, but certainly not least, my colleague Kyle Anderson, who I stole about half of these slides from, at the California Volcano Observatory, and his co-authors tracked the evolution of the magmatic system from a really steady elastic decompression to that elastic failure that we were seeing as when we saw those collapse events. And through statistical Bayesian modeling, they were able to estimate the location, the geometry, the volume, and the time evolving pressure within the reservoir as those conditions, as well as the conditions required to trigger the failure of that overlying crust, that piston drop down that we looked at earlier. Now, all that being said, I really like to end this talk, these talks, with a few sobering reminders. Those videos are really amazing. It was really an amazing experience to be part of this eruption. There's really interesting science that came out of this, but it's really important to remember that this eruption was life-changing negatively to a lot of folks. And so I just want to end with a few satellite photos. These are Planet Lab data photos. And this is the Leilani Estates, so that subdivision before the eruption. And this is after that eruption. And it basically just wiped out a third of the houses there. I'm now going to zoom in to the Fissure 8 region. So that's Fissure 8 before the eruption. That's April 2018, pretty much. And that's after, that's August. So let me just flip back and forth. This is a little further downrift to the east of Leilani Estates. Some really nice, large farm homesteads. It's before the eruption. That's after the eruption. This is Kapoho Bay and vacation land before. Some really large farm lots. And then also, this was a big vacation community also for people within the island. So actually the mayor, Harry Kim, had a little vacation house here as well. And this is this really, World Heritage class snorkeling spot. This is before the eruption, and this is after the eruption. And so finally, what's next? Well, for the first extended period of time, since about 1983, Kīlauea is not erupting. There is no lava on the island anywhere, which makes it a weird time to be at HVO. Lava will return, but when, where, who knows? Now, while we don't have lava and we don't have a lava lake, we do have something interesting going on. That downdrop collapse portion is filling full of water, and it's slowly meeting the groundwater table. And so we currently have the world's youngest caldera lake. It's been growing since about the beginning of July 2019. We were flying LiDAR out here, our contractor was flying LiDAR out here as a post-eruption survey, and noticed a small pool of water in the bottom of it in July. And it's been growing ever since. And so it's now almost 50 meters deep. It's got a volume of about 770,000 cubic meters. It's infilling at about 32 grams per second, kilograms per second, and that continues to increase. How deep will it get? It could be another 20 to 30 or maybe 50 meters. It's hard to tell. The groundwater table is very complicated there because of a bunch of vertical dike structures. It has some significant implications in terms of the possibility of explosive eruptions going forward. And so while we don't have lava on the island, it is definitely keeping us busy. And with that, I'm happy to take any questions.
Thank you, Ashton. That was an excellent presentation. So if anyone has any questions, you can feel free to unmute yourself and ask, or you can type it into the chat and I will read it aloud. I know we're over time a little bit, so if you have to go, that's also okay. So I see. So from Chris Tonkin, she asked, were any of the petroglyphs lost?
Not that I'm aware of. So a lot of the petroglyphs are much closer to the summit. They're kind of between the summit and the coastline. So that's kind of where the petroglyphs are in terms of the road down to the coast. Whether petroglyphs were lost that were undiscovered, possibly, but not the main source of petroglyphs that we usually think of when we think of the Hawaiian ones.
And Dale Chase asked, where does Luihi fit in this puzzle?
That's interesting. Luihi, following this, did have some increased seismicity in 2019. So we had a few swarms, and those were some of the first swarms that we've had in quite a while, in a number of years. So no direct interaction between what was happening, because most of everything that was occurring in 2018 were shallow-driven processes. But along with that Luihi swarm that we had last year, we've also had, last few years, a dearth of seismicity in southwest of Kilauea in an area called Pahala. And so the seismicity in Luihi and the seismicity in Pahala might be indicative of deeper changes in the magnetic system coming up from the mantle between 40 and 20 kilometers. But if anyone wants to go map Luihi again, let me know. I could use a seat on the boat.
Okay, any other questions? All right, well, thank you, Ashton, again. We really appreciate your time. And with that, I hope that everyone has a safe and enjoyable Thanksgiving break. And we'll see you guys again on December 4th.